Hi guys, in this video we're going to talk about physical pendulums, which are great fun. I really like physical pendulums. They're not very different from regular pendulums, but then again they are, so let's go ahead and talk about those. Okay, so what we're going to start with is we're going to kind of compare them, and then we'll draw some pictures, and then we'll look at those equations that we've been looking at for all the other simple harmonic oscillators that we've been looking at. So a standard pendulum is when we have a mass on a string, that pendulum bob that swings back and forth. The main difference between a regular pendulum and a physical pendulum is that we have a whole object that is swinging. So like imagine if we had like a broom or what do you call it? That thing that rotates with a clock. That what do they call that thing? I can't think of its name. Drawing a blank. It's okay. Anything else that you might swing, or like a person on a swing, that might be more of a physical pendulum instead, although the swing that it's on is not very massive in comparison. So something like that would be a physical pendulum. So I've got one that I've got under this red box here that is a physical pendulum. It's just a blob, actually. My physical pendulum example is a blob. What happens is that because that entire shape is rotating, instead of just the gravitational force being the restoring force, we've actually got some torque that's playing a role, but that torque is changing, so it's not just a constant torque the whole time, because that torque is a result of the gravitational force. So let's take a look at this picture here, and if you need some time to draw it, pause the video. There we go. Okay, and I'm going to zoom in here real fast. So here's my blob. Okay, one of these blobs is green and the other blob is kind of purple. Okay, so the green blob is where it would be in equilibrium. Let me kind of label that. Oh, it's going to zoom back out. Okay, so this green blob would be equilibrium. Okay, and then we're pulling the blob up to the purple here, which is where our maximum is. So this is where we're going to take it up, and then we're going to release it. So that's our amplitude. Okay, and then after we've done that and we let go, it's going to swing, and we've got like a pin or something holding it right here. This is our point of our pivot point here, that O. Okay, but our blob has a center of mass that is marked here with that CM, and so the torque is going to be applied at that center of mass. So it's going to be rotating about O, but the torque is going to be applied at the center of mass. Now, remember, our pendulum has just a string. That's a straight line, by the way, with a bob at the end. Those lines are exactly the same, and it's going to swing back and forth like this. And it's very similar because we've got gravity here, but our center of mass is right there, and so our torque doesn't really, this is a very similar situation, but it's just a little bit different. Okay, I'm going to erase this really awful picture over here. We don't need to see that. Okay. Oops. Forget that it does that now. So we've got this here. So I've marked some other things on the picture here. Oops. We've got our initial angle, that theta right there that we're pulling it up to, and R measures the distance between the center of mass and the point of origin. And then we've got that R sine theta, that's that what do you call it, that perpendicular distance from the force to that point of origin, and then we've got our FG on there. Okay, and so when we try to do our measurements, we're going to be looking there. So we're going to look at the same set of equations, and we're just going to put in what we know. Okay, so instead of just the plain old force of gravity, we are going to put in a force of gravity, but our force of gravity is going to have a magnitude, or the torque is going to be dependent on the force of gravity, which is going to have a magnitude of mgr times the sine of theta. Okay, and that's because we're dealing with a torque here. We're looking at the torque mgr sine theta for that object there. It's the r sine theta is that that lever arm that we're dealing with, and the torque is also found using, oh goodness, my dog is getting into trouble down the hall, is found also using the rotational equivalent of Newton's second law, and so we've got that there too. So we're gonna combine those two things right here, and so all I've done is I've written those two things. Now the negative that's on there is because of it's a directional thing, right? So it's moving in that direction toward to the left here. So that's why we have the negative. Oops, I'm trying to erase stuff and it keeps going back. I have to push that button every time. It's okay. All right, so what I've done here is I've replaced that alpha. Remember that alpha is just the second derivative of the change in theta. And the reason that we're doing this is we're trying to get it into that same format of that we've been doing on all these other simple harmonic motions, where we're trying to get it to look like that second derivative of the position. And so here we have a position right here, and here we have the second derivative of the position right there. But we need it to kind of follow that same format, remember, that looks like this one, right? No, not that one. We need it to look a little bit closer. Hang on, we're gonna do that one. Yeah. So we got the theta out of there. Oh, it's this one. Gosh darn it. It's this one that we're trying to get it to look at. The alpha, the A equals minus omega squared x, because it's the second derivative of that displacement. So we're nearly there. So we've got our alpha, here's our A, and here's our x. We just have to get it to have the omega squared all together. So we're gonna do that. We're gonna do that next. So our sine theta is theta for small angles. Remember, that's like less than 15 degrees. And then when we rearrange that to have the same A and x right there, now you can see that we have omega squared. So we have that same format. And hopefully you can see that, whoops, omega squared. Okay, I'm trying to erase stuff, but I'm just writing instead because my eraser goes away. There we go. Instead of theta, we have x. Okay, and so we have our omega squared, without that negative, is mgr over I. So we were able to find an omega squared for our physical pendulum, just like we did with the other things. So now we can use this to find our period. Okay, now remember, our period is 2 pi over omega. Is that right? 2 pi over omega. And so when we plug in omega, which will be the square root of mgr over I. Gosh darn it, I'm drawing a line again. Nope. There, nope. There we go. Then we'll have 2 pi over the square root of mgr over I. And when we solve, when we flip that fraction in the square root upside down to be on top, we'll have 2 pi times the square root of I over mgr. Remember that I is just the moment of inertia of the whatever blob we have. We just have a blob up here, but it could be a hammer. Maybe it's a ruler, because a ruler is not, I mean, it can make a good pendulum, but it's not actually a pendulum. In fact, a lot of the pendulums that I've seen in AP Physics C mechanics problems with this one are a ruler or a rod that is rotating. And so, in fact, we will be doing a lab that includes a rod that is swinging, which will be loads of fun. And then you can also find the frequency from that, which would just be the inverse, right? So it'd be 1 over 2 pi times the square root of mgr over I. That would be the frequency. We can write that down real fast too, if we want to. So F would be 1 over 2 pi times the square root of mgr over I. Okay? And so that's it. That's all there is for physical pendulums. And just knowing where that came from is the most useful thing to do here, okay? Any questions about that, you can make sure you ask. I'm sorry I'm not there today, but there should be some practice assignments for you to work on as well, and that's all I have for that. Okay, thanks for watching.